Hello everyone. So the target that we have in this lab is to acquaint you with the with the different type of theories that you'll be reading in your theory class, and we like to show you the implications of the theory in practical life. So we will be doing it with the help of a servo system. So this system, the figure that you can see is called the servo system. Here, these things are motors. These motors have the capability of run, and using this system, you can control the speed and direction and positions of it. Uh, there are certain things that you need to see in basic servo system. So this part over here is called it's a shaft that engages or disengages the output potentiometer. When the shaft is turned outwards, the output potentiometer is disengaged. When the shaft is turned inward, the output potentiometer is engaged. Now, what is output potentiometer? Output potentiometer is a device that will actually measure the position of the system. That is, when output potentiometer is engaged, the system's position will be measured. When the output potentiometer is not engaged, the system's position will not be measured accurately. The thing you see here is an eddy current brake. So this disc you see here, this is actually a metal disc, and this thing over here is a magnet. So when you lower this thing, what will happen? The magnet will stop the metal ring from moving. So magnet will push the metal ring, and it will try to stop it. So as a result, a brake will be provided on the metal ring. So this is since the brake is created by eddy currents, you surely would have learned about eddy currents in your machine theory. That is triple E two three 221 and 223. So this brake is called eddy current brake. Now this motor rotates. Here there are gears and there are belts. Through the belts it rotates different kinds of gears. Here you can see the velocity of the motor at all point of time. Now that you find here is not always perfect. The reason behind this is maybe the velocity changes too quickly and this display is not updated as quickly. Now, other things that you need to learn, you can see there are a lot of LEDs here, and this disk is patterned. The pattern of this disk added with all these LEDs and photo receivers will indicate the position of actual motor. That is, at any point of time, you need either you can see the pattern is either silver, which can reflect light, or black, which cannot reflect light. So if the LED is turned on and light is reflected and it is detected, then what happens is it will understand that in front of LED whether there is a silver patch or a black patch. And by finding whether there is a silver patch or a black patch, it can determine the position of the actual rotary system. So position control is done through these photodetectors and photodiodes. All the information that you'll be receiving from here will be passed through this portal, which is the interface module. It interfaces the computer with the system. So all the data, all the information of it, for example, speed, velocity, error, position, whatever it is, all this data will be passed through this module, and this module will pass the data to the computer. And this is called output potentiometer. This is used to provide an external output signal to the external input signal to this device. So in this course, we actually would not require the output potentiometer. The power is provided with the help of a power supply. If you look at your lab sheets that have been provided in Bucks, you can see the connection diagram of it. Connection diagram is very easy. You can just look into it and you can connect it on your own. That won't be creating any problems. Now, the thing is, the greatest problem we have here is we actually do not have this board at our hand, so we actually cannot see how this is operating. The good news is you don't need to see it. I mean, yes, you do. You don't need to see it on your eyes. You can see it in the video and you'll understand everything. Because we are seeing how the motor reacts, but we are taking all the data from the interface module. So since we are taking all the data from the interface module, what happens is, since all the data are taken from interface modules, what happens is we are visualizing the data in computer screen. We are just seeing how the motor rotates here. So I've gone on to the control system laboratory of Bragg very recently, and I've recorded all the phenomena that you need to see. So you can see those videos and you can clearly understand what's happening. So not having the hardware will not, hopefully, will not affect your level of understanding in this course, and I really hope the course will go well. Now, before we move into a more practical discussion and how the experiment is uh, going to be conducted, we would go into a bit of theoretical discussion that you're supposed to learn in theory class, but I'll be teaching them in the lab class as well. So the title of the first experiment is time response analysis. So the title is time response analysis. Okay, now what is time response analysis? So what we do here is we have a motor. So suppose this is our motor. We provide an electrical input, suppose a voltage, and we get speed as output. So the input is electrical voltage, output is speed. Now, what it does is the outputs in speed, we can only see speed, but we need uh, some way to measure the speed. So what it does is there is a tachometer connected to this motor. This what it tachometer does is it measures the speed and it converts it into a voltage. So what we get input as a voltage, and we get output as speed, which is represented by a voltage. Okay. Now, obviously, let us take an example of fan. When you switch on the fan, does it rotate at maximum speed from the very beginning? No, it doesn't. What happens is it slowly rises to the maximum speed. Then what happens if we provide an input in this way, that is, we suddenly turn a switch of a motor on, what happens is if this is our voltage input, then the output speed will follow a curve like this. It will slowly rise. So if output speed follows, why am I mentioning V out output speed as voltage? Because I'm considering there's a tachometer involved, which is converting the speed into voltage. Now the output voltage is this, input voltage is this. Now there are two determining or key factors here which we need to understand. One thing is gain. What does gain mean? Gain means actually the ratio of the output and the input, that is V out by V in at the steady state. That is, suppose you have turned the fan on and for about 5 minutes now. Now, fan should be in the maximum speed, and according to the rating of the fan, you have provided 220 volts, so maximum speed should correspond to 220 volts, but it is seen that maximum speed is actually not 220 volts, but it is rather 200 volts. I'm saying speed in terms of volt because of tachometer, you understand that. So our gain would be 200 by 220. So the gain will be less than 1. So the gain is a thing that is actually dependent on the steady state of the output. That is when the input has been exerted for a long period of time and the output value is fixed. And there is another factor, how fast does it reach the maximum value or the steady state? That is another concern. And that is defined as time period. So in time response analysis, what we do is we use a black box approach. Black box approach. Now what the black box approach is, this is a black box. What we mean by black box is we do not know what's inside this box. We have no clue what's inside this box. We will provide an input. We will observe the output. So what happens is we are providing an input and we are getting the output, and we will be comparing the input with the output. So obviously, since this is a servo system or any system in the world, it may be as simple in a system as a fan, or maybe it may be a crane, it may be a lift, it may be anything. Whatever the system is, it will have two characteristics. That is, in order to define any physical system in the world, we can use two parameters. The two parameters are gain, that is the steady state response, and time constant. So if we know the gain and time constant of the system, we do not actually need to care what that system is. We do not need to care what the system is. It may be lift, it may be a fan, it may be a crane, it may be anything else in the world. It may be an AC as well. We do not need to care about it. As soon as we know the gain and time constant, we basically know everything about the system, and we can control the system in ways, in different kind of ways. We'll be learning about controlling the system in our experiment 3, 4, and 5. But experiment 1 and 2 deals with modeling the system. Modeling the system means experiment 1 and 2 uh, actually works with associating an equation with the system. The equation is in terms of gain and time constant. So any system, since can be defined by two variables, gain and time constant, our first responsibility would be to measure the gain and time constant. So at this stage, we have, let's move to the software part of it. Now, the software is provided. As far as I remember, in your software, there is no necessary to install it. I might be wrong. You can check it. You'll go to VCL, Virtual Control Laboratory, then you'll go to CD1032C. Inside that, you'll go to VCL, this folder. Inside that, you'll go to VCL application. When you open it, it will say the hardware interface has not been detected. Obviously, we do not have the hardware at home, so it will run in simulation mode. There is no problem about it. Now, let us move to our actual lab sheet and see. So, in the lab sheet, we can see that at first we can look at the procedure. First, the system should be wired with the standard, and okay, we have wired it. Then there is this thing provided. So, we have to look into this thing. So it says to open the file this. Actually, in these files, the file names, we have already established this system or set up this system. Still, I'll show you how to set up this system on your own. So if you look at VCL, now here you have, if you look cozy, here you have, if you load the setup with CA06P03. After loading it, you can see that the signal is stepped, the level is 60%, offset is 0%, rate is 20 milliseconds. Okay, now we need to determine what these things are. So the unknown factors here are signal, level, offset, and rate. These four unknown things we need to know. So again, what we're doing, I'm writing it in the corner. We want to find the planned gain, which we which we denote as Kp, and we need to find the time constant. We denote this as tau. Now, what we need to do is, at first, we have signal. Signal is step. Then we have level, 60%. Offset, 0%, and the last but not the least is rate, 20 milliseconds. Now, signal is step. What does step indicate? Step indicate that there is a rectangular pulse involved. That is, the voltage abruptly changes from one value to another value. For example, In this case, it abruptly changes from negative value to a positive value, remains steady in that state. Then again, it abruptly changes from positive to negative value and remains steady in that state. So this is how the step works. Step is abrupt change. If you have taken the course of signals and systems or DSP, I think the steps should be very clear to you. That's no problem. Now the level is, this is a, suppose this is our zero line. So if this is a zero line and our system is a digital system, that is 5-volt system. If the system is 5-volt system, 60% of 5 volts is 3 volts. So this level will indicate, since the system is stepped, the level will indicate that the positive value is 3 volts above 0 and the negative value is 3 volts below 0. So here we have minus 3, here we have 3 volts. That is, our step response is, it goes from 3 volts to minus 3 volts. Offset means how much the value is, uh, how much DC shift is provided to the value. For example, here offset is 0. It will mean that since the level is 60%, the this level, the positive level is plus 3 volts and the negative level is minus 3 volts. Now, if we consider our offset is 10%, if offset was 10%, then what would have happened? Uh, it would have happened 10% of 5 volts is actually 0.5. So what it would do is it would make the positive value as 3.5 volts and negative value as minus 2.5. That is, it will DC shift the entire waveform by 0.5. Rate is 20 milliseconds, means it takes one reading in every 20 milliseconds. So I hope all the parameters, step, level, offset, rate, all of these are understandable. So in this signal, you'll be seeing that there is step and there is also DC value, there is sine and other things. In case of alternating signals, for example, step and sine, these things, the level indicates the positive and negative values, and offset indicates the DC shift. In case of DC value, if the signal is chosen as a DC source, then what happens is whatever is there in the level, it does not matter. Only the offset matters, and offset is the DC value associated with it. Now let us look at the simulation software to understand what we are actually getting at. So this is here the level is 60%. So we can see that this is a 5-volt system. This is our 0, 1 volt, 2 volt, 3 volts. We have 3 volts in positive and again minus 1, minus 2, minus 3. So minus 3 volts in negative. So this line here is our input. This line here is our output. Now, if we increase the level to say 10%, then what happens? You see, or say 20%, we're increasing the level by 20%. What happens is input becomes from 3 input goes to 4 because 20% of 5 volts means 1 volt. So the positive part of input has risen by 1, that is it's 4 volt, and the negative part is now minus 2 volt. So the entire thing is DC shifted by 1 volt. Uh, Again, if you choose DC level, you can see that in DC level, this is 0 volt, this is 1 volt. So the effect of level is not there. Only the offset of 20% is active. So we do not actually need the DC level. We need the step response, and we can turn the offset to 0. Now, when you provide this as input, that is a 3 volts input, and what you'll get is in the this part of the cycle, since the voltage across the motor is positive, the motor will rotate in one direction, and in the other part of the cycle, since the voltage across the motor is negative, the motor will rotate in the opposite direction. That is, for the first half, it will rotate in one direction and reach a steady state. Then suddenly it will start rotating in opposite direction and reach a steady state there as well, and it will keep on continuing. Now you can look at the video at the right right top corner, and you see that the motor is at one cycle it's rotating towards one direction, and in another cycle it's rotating towards the opposite direction. So I hope you understand what it means. Now, if we change the offset by say, uh, sorry, say if we change the offset to 20%, then what happens is, you see the positive voltage is 4 volts and the negative voltage is minus 2 volts. What that would indicate? That would indicate is that in one direction the motor will run very fast because the voltage is more. You know, in a motor, the more voltage you provide, the faster it rotates. So in one direction, the motor will rotate very fast, and in the other direction, the motor will rotate very slow. If you look at the video, you'll be seeing this phenomena very clearly. Now that we understand how these settings work, and we need to understand it really well, uh, we can change to our original settings, which was level 60%, offset 0%, rate 20 milliseconds. Now we need to determine the gain and time constant. Now there is only one way of determining gain, which is really easy. What we do is, first thing is we freeze the system, freeze, and we wait. After pressing freeze, we have to wait. After waiting a bit, we can see that frozen time. This thing will come. Here we turn on. If we turn on, what happens is, suppose, what happens is you can see here that amplitude A. Now we click this portion, this 2.5 portion, and we click here, and we align with the input, and B, we click here and it align with the negative part of the input. So this plus 3 minus 3, that is, there is a difference of 6 volts. We call this 6 volts as input span. So input span is equal to 6 volts. Now similarly, going into the software, what we can do is we click A and click the uppermost part of output, click B and click the bottommost part of the output. Then what we find is plus 2.750 and minus 2.750. The difference between these two will actually be our output span. Now the output span is 5.5 volts. So what we can write here is, you see you have these things there in data table. You have to write it there. Output span is equal to 5.5 volts. So our gain Kp is equal to output span divided by input span. This is our gain Kp. Whatever the value is, volts will get cancelled, and you'll have a fixed, we have a constant number. So this is our gain Kp, which is also called plant gain. Now that we have measured gain, the next thing left for us to measure is the time constant. Now there are three methods of determining time constant. Okay, at first let me erase this out. So there are three methods of determining time constant. The first method is initial slope method. The second method is settling time method. And the third method is 63% method. So we'll be learning all the three methods. This initial slope method and settling time methods are actually approximation, and 63% method is the exact method. That is, it gives the most perfect result. Now, let us just look into mhm. let us just look into our simulation file here. So at first, what we need to do is we need to find the time constant by initial slope method. In order to do that, what we do is we select this B and we place it at the bottom level, that is the bottom level of the output, so which is uh, here, minus 2.750. After we do that, we select this slope option. We can click slope and we just move this slope above. And we move this slope in such a way that that slope, this line over here, will be sloped to the output curve. So here we can see that this line is the initial slope of the output curve. Since we are taking the initial slope of output curve, that is why it is called initial slope method. Now, this slope will intersect with the input curve at one position. Let us click this time variable, and if we click it here, so this is the position where this initial slope curve intersects with the input curve, and this is 0.28. So in this initial slope method, our time constant is this 0.28, that is 280 milliseconds. So initial slope method, we get 280 milliseconds. And now the second method or second approximation method is the settling time method. The process that we follow in the settling time method is that we see that uh, the actual theory of settling time method is that generally the output sometimes has overshoot. You must have learned it in theory classes, and this is the steady state value. The settling time is the time when the output reaches to plus minus 2% of the steady state value, and it does not get outside that. That is, for example, this is in this case it reaches plus minus 2%, but at one stage of time it goes above it. But once it has settled, it will not the value will not fluctuate beyond plus minus 2%. So that is the settling time. In these cases, this type of damped condition will actually not get the accurate settling time, and the big problem with this is that uh, uh, the the what we can say, the graph is not coarse enough, or the graph is not fine enough. So we cannot measure the exact value where we get the 0.2% time. So what we do is we click a position where we can see that it has settled. For example, here we can see that the graph has settled. So normally the definition of time constant tau is equal to settling time divided by 4. But since we are not being able to find that plus minus 2% mark, and there will always be error because we are looking at the time at which the graph has already reached the steady state value. So as we can see from this graph, it reaches a steady state value after it reaches settling time. That is, it attains a steady state value after settling time. So in this case, our tau would be better approximated by settling time divided by 5. That is steady state value time divided by 5. So why are we using the approximation? We are using the approximation because the software that we are using, that does not give us the correct, that does not give us high enough resolution to find the accurate settling time. So what do we do? It's 1.16 seconds. So 1.16 divided by 5 is 0.232. 0.232. So by settling time method, 232 milliseconds. This is actually the time constant. And so we have learned the initial slope method where the initial slope intersects the input, the time of that point. It is to be remembered that time constant is time. So we go to the place where the graph reaches the steady state and we actually measure the time, that is the x-axis and not the y-axis. Similar is the case of initial slope method. The initial slope intersects with the input. We measure the time of it, that is the x-axis, and not the value in the y-axis. A lot of people tend to forget it and tend to make mistakes. So this must be very carefully observed. that we considered the x-axis, that is the time value, which is the settling time. Now, the third method that we'll be seeing is 63% method. Before we go on to 63% method, I would like to state that 63% method is actually the most efficient, or it gives the most accurate, it is supposed to give the most accurate value of the time constant if our calculations are correct. This is because the time constant is defined as the time taken by a system to reach 63% of the final value. So the definition of time constant matches with the 63% method. These two are that's why called approximations. Approximations. Definition of 63% method is the time taken to reach 63% of original value. So here what we need to do is we need to find a value, 63% value. That formula of 63% value is bottom level of output plus 63 by 100 into output span. So this is the formula of 63% value. Now, 63, if this is the formula that we use, so here we can see that the bottom level of output is minus 2.750. So we can write minus 2.750 plus 0.63 into 5.5. If we make this calculation, we will find 0.63 into 5.5 minus 2.75. The value that it gives is 0.715. It is to be noted that this is also volt, this is also volt. So 63% value is actually volt, 0.715 volt. This is not the time constant. The time constant is, what we do is we take this A and we find the value of 0.715. So now the resolution is not good enough that we'll find 0.715. The resolution is just enough so that we can get 0.7. So 0.7, we have found the 0.7 this line, and we take the time and we just bring the time at exactly the value, exactly the place where the value of output is 0.7. Again, I'm saying it was supposed to be 0. It was not supposed to be 0.7. It was supposed to be 0.715. But still, it gives since the resolution is low, it gives more or less a good approximation. So, uh, it, so I am clicking this into 2 so that I can zoom into it, and by zooming into it, I can just change it. This is our 0.7. This is our 0.7. So this almost gives 230 milliseconds. Here we can see that they intersect at 230 milliseconds. So by 63% method, our time period that we find is 230 milliseconds. Now, one thing is to be seen. I am claiming 63% method is the closest to the correct value. But what is the validity? You can find the validity from here. Here, the value which is used here, which is put here, it is the actual time constant, which is 225 milliseconds. And the closest to 225 milliseconds that you obtained is 230 milliseconds. Obviously, you are not able to obtain the exact value because of low resolution associated. So this is the closest one, and our value of time constant becomes 230 milliseconds. One thing is to be noted, planned gain is 0.916 milliseconds according to our calculation. And if we go here, our planned gain is actually 0.92 milliseconds. So which is almost the same. That is, the calculations that we have done is correct. So in your report, you'll be modifying these values. How you'll be modifying these values, I'll let you know, and no problem with it. And you'll find different values and you'll do your calculation. So you'll be modifying the value before simulation. You'll be modifying the value of KP and time constant according to your student IDs. I'll be telling you how to do that. And by modifying, after modifying these values, you'll find out the time constant and gain, and you'll just try to you'll just see that whether the time constant and gain that you found matches with the value you have put here. Okay, so there goes the discussion about your report. And this is the second part of the first experiment, measuring the time constant. Now, once we know our Kp, that is the plant's gains, and tau, the time constant, we actually know everything about the system. That is our black box, which is our servo system has been modeled. Servo system has been modeled with Kp is equal to 0.916, tau is equal to 230 ms. One thing is to be noted that, as I said, by modeling we mean attaining a way using which we can define the response mathematically. What do I mean? By this I mean if you put a sine wave as an input, if you put a step as an input, you get a response that can be defined by both Kp and tau. How can it be defined? It can be defined by the formula output is equal to Kp into 1 minus e to the power minus t by tau. So output is equal to Kp into 1 minus e to the power minus t by tau. By this formula, you can actually determine the output. So if you plot, if you know the Kp and tau and you plot against t, you get an output like this, which will be similar to the output that we obtained from graph. Okay. So this is the underlying equation of a black box or a plant or a system, whatever the system. It can be fan, a server system in our case, or anything else. Now, this is what we are talking about. We are measuring the velocities till now. We have only worked with velocities, and now another thing that we need to consider is position. Now, till now we had input as voltage, output as velocity, which has been converted to voltage by tachometer. So now we know that V is equal to ds dt. So in order to get distance or the position from velocity, what do we need to do? Obviously, we need to integrate. So from the velocity information, if we need position information, we'll be needing to integrate. So since we'll be needing to integrate, since integration results in a constant, so we'll get S, or the position, is equal to integration of V dt plus C, integration constant. This C is here termed as Ki, or integrator constant. So whenever in the servo system we are converting velocity into position, then you will be needing a constant Ki. And next part of our experiment is to measure Ki. So what we first did was we first modeled the servo system or the motor itself, and now we are modeling how we can convert velocity into position. Now, in order to do that, what we need to do is we need to go to our VLC. If you check our lab report, if you check our lab manual, you can see that here we need to bring some changes. The changes are signal level is no longer step. Signal level will be DC level. Then the level is 60%, which is right. Our rate will be 10 millisecond and offset would be 40%. So we decrease the rate and we increase the offset. So after doing this, it is frozen. So what we need to do is we need to click freeze and start. After we put start, we'll see an output like this. So our input is a DC and output is also a DC. In this case, the motor will run in single direction. As you can see in the right top corner, you'll be seeing a video where the motor runs in only one direction. Here the motor is not changing the direction because only the positive voltage is provided. So the positive voltage is provided. And what is the amount of voltage? Since offset is 4%, 4% of 5 volts is 2 volts. So the positive voltage across the motor is 2 volts. Now what we need to do is we need to uh, switch off the input, switch off the position, switch on the position, switch off the velocity. We can keep the velocity. We need to switch on the position. Now let's freeze it. Now one thing is to be noted. You can see that the position graph here is a sawtooth wave. Why is this a sawtooth? The position is constantly changing, then why is this a sawtooth wave? This thing needs to be understood. The reason behind this is what it does is this is a motor, right? Suppose this is rotating in this direction. So what happens? The angular rotation is changing. It's increasing, increasing, increasing. And at this point, the angular rotation is maximum. That is 360 degree. At this point, the angular rotation is maximum, 360 degree. And 360 degree inherently also means 0 degree. So from 360 degree, it jumps to 0 degree and starts increasing again. That is from 0, it goes on to 360. Then it sudden, that is from 0, it increases to 360. Then suddenly drops back to 0 and again increases to 360. So that's why it's like a sawtooth wave. Now, if you look at the data table, in the data table you'll find that there is a phenomena mentioned called there is a phenomena mentioned which is called V well. So what this V well is? V well is this output voltage. That is, if we time the timer on, we choose A and we align A with this output, we get A is equal to, sorry, this is not the output. Here it's the output. So we get A is equal to 1.85. So our V well that you that we would put in the data sheet is V well is equal to 1.85. That is number one. Now we need to find that integrator gain. In order to find that integrator gain, what we need to do is we need to at first choose A and take it a position of minus 4 volts, and we choose B and take it to the position of plus 4 volts. So A is taken to minus 4 volts and B is taken to plus 4 volts. Then what we need to do is we need to take the we need to take the time of B. The time of B is 1.025. So let's note down. Time of B is equal to 1.025. Again, we need to find the time of A. The time of A is over here. Time of A is 0.605. So let us put sorry, this time of B. Time of A is 0.605. So changing time is equal to 1.025 minus 0.605. So this is equal to 0.42. Changing time will be 0.42. Change in voltage would be equal to, as we can see, changing voltage is minus 4. We have taken minus 4 to 4 volts. So changing voltage becomes 8. Now, if change in voltage is 8, then what we find is our slope is equal to 8 divided by 0.42. Slope means how quickly the curve goes from here to here. So our slope becomes 8 divided by 0.42. So the value of slope is 8 divided by 0.42. That is 19.04. If you check the data sheet, a position for all these things are there. We have already determined it's 1.8. Now our integrator gain Ki is equal to integrator gain would be slope divided by V well. So slope divided by V well. So it will be 19.04 divided by 1.85. So we'll get integrator gain is equal to 10.29. So integrator gain Ki over here is 10.29 according to our calculation. If we look at the value of Ky that has been put here, it's 10.3. So our calculation is correct. One thing is to be noted, you'll be changing this in your experiments. I'm just using the value as it is, but for you in your report, this value will change according to your student ID. So what we have found out is we have found out that integrator gain, and we can easily verify whether our answer is correct or not, and our answers so far are pretty much correct. Ki is equal to 10.29. Another thing is there. We need to find, as we have said, our velocity is represented in sense of volts. So we need to find a way to convert this volt into RPM. That is, there needs to be another constant or something or another method by which we can actually understand. By seeing the velocity is 1.85 volts, we can understand that in RPM what the velocity actually is. So in order to do that, what we need to do is, let's write here V well is equal to 1.85. Let's keep it. So the velocity, as we know, V is equal to distance by time. Velocity is equal to distance by time, as simple as that. So let us just look and check how much time does it take for it to complete one cycle. That is, how much time does it take to start from 0 degree, roam around and come back at 0 degree. How much time does it take? So in order to do that, what we do is we first select we find the time of this plus 4 volts here, which is we have measured it earlier, which is 1.025, and we measure the time here, which is 1.565. That is, in order to complete one cycle, the time it takes, that is time period, is equal to 1.565 minus 1.025. That is, the time period is 1.025. The time period is 0.54 seconds. Now, since the time period is 0.54 seconds, that is, for one revolution, it takes 0.54 seconds. So if we get 0.5, if it takes 0.54 seconds for one revolution, it takes in 1 second it can revolve 1 by 0.54 times. In 1 second it completes auto revs. So in 60 seconds or 1 minute, it revolves 60 divided by 0.54 times. So 60 divided by 0.54 is equal to 111.11, 111.11 times. So this is our revolution per minute. So our RPM is equal to 111.11. Now another thing is to be noted that this RPM is ATHO 111.11, which is converted into voltage V well is equal to 1.85. So 1.85 volts means 111.11. So 1 volts will indicate 111.11 divided by 1.85 revolutions per minute. So 111.11 divided by 1.85. So 1 volt will indicate 60.05 revolutions per minute. RPM. And this 60.05 is denoted by another factor Kr, which is 60.05. So if the velocity volts that we obtained, that is the output velocity, at any point, if we measure, if we multiply V well with Kr, that is output velocity in terms of volts, if it's multiplied with Kr, then what we get is RPM, that is the speed of the motor. So this is RPM by volts unit. So if we know the Kr of the system, this constant of the system, we can easily convert the velocity from volts to RPM unit. RPM is the RPM is the established unit for velocity. Volts is not a unit for velocity. So by determining this factor Kr, we are actually determining the speed of it. Another thing which you'll see is the effect of load. That is this gain and everything. This is an open loop system, right? If you look at the system, this is an open loop system. You put an input, there is a gain, and that's everything else. There is open loop system. There is no feedback. Since there is no feedback, we'll observe that the speed will drastically fall when the speed will drastically fall when actually the brake is applied on the motor. And for braking, we use that eddy current brake. You can look at the right top corner. In the video, you'll see that whenever I'm applying the brake, the speed is drastically falling. So this is the disadvantage of an open loop system. In an open loop system, what happens is there is no control. That is, if you apply a brake, the speed will fall. That is, it is an uncontrolled system. In the later experiments, when we actually go on to build up our controllers, we'll see that when we build up our controllers, we'll see that uh, even when we apply brakes, the change in velocity will be very low. So that will indicate that our performance in a closed loop system is being improved. That is all for this experiment. So if we just look back what we learned from this experiment and just recap it a little bit, let me erase this portion. So the target of this experiment at first was modeling a plant. In this case, the plant is servo system. Plant is whatever that performs the work or moves, that is the servo system here. Again, to converting velocity measurement to position. How do we do that? By finding the integrator gain Ki. And the third part was comparing V well with RPM. That is comparing the voltage with actual speed. So when you go on to do this experiment, you'll have your own Kp, tau, and Ki, and you'll have a different value of V well, you'll have a different value of Kr maybe, and you'll put this Kp, tau, and Ki into the system. That is, if you see here, you can change these values. So you change it accordingly, and you'll find the results accordingly. You have to put screenshots of each and every system, each and every calculations that you're taking. You have to put a screenshot, otherwise I'll not be understanding whether you have done it or not. So you'll have to put a screenshots of all the systems in the report, and in the report you'll also have to answer certain questions. The questions will be given in box, and for setting up this whatever this is, setting up this KP, time constant, and KI, you will be using your student ID. You'll be using your student ID in this way. So I'm taking a random student ID from your list, 16321141. Suppose this is a random student. Okay, 0141 041 1041. So this is a random student ID. Suppose this is your student ID. So what you'll do is you will choose the last two digits as your last three digits as your KP, and these last three digits can be it actually depends with last two, sorry, not last three digits. You'll choose the last two digits as KP. That is, KP is equal to 0 point last two digits. And for example, here KP is equal to 0.41. So if we look at here, we turn out the position. Suppose we go back to step here and decrease this. So KP will, for this case, KP would be 0.41. So KP would be 0.41, something like this. One thing is to be said that if this digit is 0, then what we do is you neglect this digit and choose these two. For example, if your student ID is 16321301, then your KP would be 0.31. Okay, so this is your KP. Then you'd need the time constant tau. Tau would be the first three digits. This is tau in millisecond. And then you'll require KI, which is a 4-bit number. 4-bit number would be, if you leave two digits from first and two digits from last, this is your KI, 30 left side, point right side. Now let us actually check whether in simulation you can make it 30 or not. So okay, in simulation you cannot make it as high as 32.10. Then what do? If this is the case, then you just neglect this 3. You'll make Ki is equal to 2.10. So we can do that here. Decrease it 2.10. So this is the way, and tau is equal to 163. So by this way you'll modify your system and accordingly it'll work. You'll just, one thing is to be there, in your report you'll be mentioning your student ID, and from student ID you'll point out your value of KP, tau, and KI that you'll use in your actual simulations, and you'll determine all the values. That is, you'll determine the experimentally found KP, you'll determine tau, KI, VWEL, and KR. Then there will be certain questions. You answer all these questions and submit it as a report. The report will be computer typed. That is, you have to type in Microsoft Word and convert it into PDF, and you will be uploading the report in Box. That's all for this lecture. In the next lecture, we'll be learning about frequency analysis.